In this animation, we begin by visualizing a shock absorber consisting of two springs, one nested inside the other. A mass is dropped onto the springs, making them compress. Here we see a 2D view of the previous setup. The mass is dropped with an initial velocity Vm from a height h. The mass gains kinetic energy while falling, and upon reaching the springs, it causes them to compress by the distance x. The outer spring has a stiffness denoted by Ko, and we have to determine the stiffness of the inner spring Ki, given that the other variables are known. We know from the conservation of energy that the total initial energy equals the total final energy. This means that the sum of kinetic energy, gravitational potential energy, and elastic potential energy is equal for both initial and final states. The initial kinetic energy is half m Vm squared because the velocity of the mass initially is Vm, and the final kinetic energy is zero as the whole system is at rest in the final position. When determining the gravitational potential energy, we can simplify the calculations by selecting an appropriate zero reference of our choice. We choose the height of the final spring position as a zero level, which makes the initial gravitational potential energy as mg into h plus x. Since the springs are not compressed in the initial state, the elastic potential energy would be zero, and in the final state, the compression x results in the elastic potential energy of half ko x squared for the outer spring and half ki x squared for the inner spring. After simplifying the equation, we can then solve to find the unknown variable ki. As you can see, through careful application of the principle of energy conservation, such questions can be easily solved.